To me, it's easier to figure out the problem than to use a formula. This is our jury example. You know, you've got 10 males, 15 females, you pick 7 people. What's the probability of getting 5 females? This is what the hypergeometric distribution would be. What would you have in the denominator? As far as the total number of different ways I could pick people. 25 choose 7, very good. And what would I have in my numerator? Yeah, so 25 choose 7, 10 choose 2, 15 choose 5, right? And that gives you the probability. There's a formula in your book for this, but like I said, to me, it's just easier to figure out the probabilities counting-wise. So that's the hypergeometric distribution. It gives you the mean and variance of the problems. Let's go now to the Beatles. Oh, let's go with the chord. The chord. Actually, is that the... Nope, that's not the chord. Sorry. Let's try this one. See if it works.
Wake up with Hardee's. Hardee's new $3 hot cake breakfast sandwich. A full breakfast.
Yeah. I have to take this out on the video then.
Wake up, you're happy with the new Hardee's $3 hot cake breakfast sandwich. Feed your happy.
The next song we'd like to sing.
Oh, it's not the chord because they're doing it live. That's all. I messed it up. Yeah, that chord right there. All right. You have to, they figured out in like the last 5 years using Fourier analysis to figure out how they actually made that chord in the remastered version. We'll try this one instead. All right, so you have an iPod playlist. They have 100 songs, 10 of which are by the Beatles. And suppose the shuffle feature is used to play the songs in random order. So the question is, does your iPod really play favorites? I talked about that time where someone thought they kept getting ABBA appearing too much on their iPod favorites, so I thought that maybe they were favoring ABBA. So what's the probability that the first Beatles song heard is the 5th song played? Okay, so the first Beatles song is played on the 5th song being played. Well, not quite, because it's not going to repeat the song. Oh. Yeah, what's your...
I'm still kind of working through this, but thinking out loud, would it be 10 choose 1 times...
You're getting way ahead of me. But okay, that's good.
I think it's 10 choose 1 times 90 choose 10. I think it's too much, is it?
Well, let's kind of figure this out. This song right here is the first Beatles, right? And you were saying that would be 10 choose 1, right?
Yeah.
For this non-Beatles one, this would be, how many choices would I have for these non-Beatles?
The other 90.
Choose how many?
9. 4.
4.
Oh, I thought we were doing
Well, it's on the 5th song being played. Okay? So this is one way that you could consider doing it. And so one way you could do is figure out this one. You could figure out what we just did here for the probability that's the 10th song being played is also that possibility as well. So it's really not that coincidental. There's like a 41. If it's one of the first 5 songs being played, oh, did I read the problem wrong? Was it supposed to be like the first one was the 5th one, but they're saying up to that point? Yeah, let's skip the whole thing. Anyway, the main thing is that you get a 41% chance that Beatles would be one of the first 5 songs being played, which is not that coincidental.
So this here, that's not complete, right? Because you have to divide by the total number of options.
Right, right. So 90 choose 4 times 10 choose 1 divided by 100 choose 5.
Yeah.
And then you'd have to do 90 choose 3 times 10 choose 1 over 100 choose 4. Yes, 99 choose 4.
So didn't we do it in the past where like you multiplied each of the chooses by their probability? Like if you knew the probability of getting the Beatles,
Right.
then like would it be 10 choose 1 times the probability of like 10 out of 100? Like 0.1.
Yeah, there's 2 different ways of thinking about it. This is a different way of you're kind of going in reverse. So there's multiple ways that you could get there. So Abby, we might be not on the same wavelength, but we can get there. I'll come back to this problem. Okay? The whole chord thing just messed me up. Instead, it was supposed to lead into the negative binomial distribution. Okay, so the negative binomial distribution you could find if you have your book right side up. On page 125. So here's the connection between the negative binomial distribution and the binomial distribution. So what's one thing about the binomial distribution? What are the 4 assumptions? Independence. Hey, we get that too. Homogeneous, that is we only have a success or a failure. And, fixed probability. Oh, it doesn't. The negative binomial does not have fixed number of trials. But that's okay because we want to distinguish it. What's the third one then?
Dichotomous.
Dichotomous, yeah. So it is still dichotomous. Each trial has either a success or failure. The difference with the negative binomial distribution is that you go until certain something has happened. So in the negative binomial distribution, you don't have a fixed number of trials. You go until you get a total of R successes. 6 boys, 6 A's, 6 fish, 12 disciples, 144,000 called people. The chosen. What'd you say? Witnesses. Yeah. 40 people sent out with swords. You just go until you get to that point. Okay, so it's not that you have a fixed number of trials. You go until you reach it. 10 free throw shots. That big three game they play in the summer. You go until you get this certain point total. Anyway, that's how you set it up. So the difference is, let's suppose you go until R successes. Let's start off with one, let's say 5 successes. Well, I'm going to have so many things, and the very last one, I'm going to put a success. This has the probability of success is P. Now, if I have failures and successes, I'm going to have to figure out all the different ways that I could have these other successes. So let's case in this say I had to do 12 probability of 12 trials. If this is the last of an S, and I've got 6 total successes, how many failures do I have?
Wait, 5 or 6 successes?
Well, we have 6 total, but since I have one S here, well, 6 failures, and how many successes do I have left for the blanks? 5. And so what's the number of ways that I could range 6 successes and 5 failures in these blanks? 11 choose 6 or 11 choose 5. So you'd have 11 choose 6. You'd still have a probability of 6, and the probability of failures would be 6. If we did the probability of 10 trials, well, the last one is success. How many failures? We still have 6 failures, right?
Yeah.
So how many do we fill in these blanks by? We had 4 failures, 5 successes. 9 choose 5. And we'd have still successes, 1 minus P.
Wait.
So we're
4.
trying to get 6 successes.
Yes, we get 6 successes, but remember the last one has to be a success.
Right. Okay, because you run at the top 5 successes. But we're trying to get 6.
Well, let's do 5, 6. Yeah.
Okay.
How about that? Does that make it better?
Yeah.
Okay. Was that your question, Jeff? Okay. Verbally and what I wrote were on different pages. So you can see the negative binomial distribution. And this one, I think the formula is nice to have. I don't think it's very easy to remember, so I don't necessarily think you remember, but how it's set up is an important part. The R minus 1 becomes, because one of your R's goes here in the very last spot. So you have R minus 1, and the X is, the way that's defined here, is the number of failures that precede the X value. So like we looked at our mini-tab counts as for the number of trials. Another way you could do it is the number of failures before you get to that point. So you have to be a little careful in setting that up. So it is sequence of independent trials until R successes have been observed. It's memoryless. There's a special case when R is equal to 1. One other thing that's kind of interesting is that if you have the sum of independent geometric random variables with the same P has a negative binomial distribution. Jonathan, that's for you for studying for the actuary test. It's just bonus information for everybody else. Now, one thing to be aware of for the geometric distribution is for number of trials to attain the first success, you write it this way, where X is 1, 2, 3. On page 126, you have the number of failures before the first success, and therefore you could start at x equals 0, 1, 2, n. So when you're looking at the mean for this one is 1 minus p over p, 1 minus p over p, and the variance is 1 minus p over p squared. But for the mean here, the mean is 1 over p and 1 over p squared. And the difference is all whether you start at 0 or at 1. Again, this is the number of trials before you get your first success. This is the number of failures before you get your first success. It depends on how you set the problem up, but you have to modify what those solutions would be. I've run out of space for the, okay, so one other distribution, and this one is very important for engineers or for computer scientists who are modeling something, and that is the Poisson distribution. It's common to modify this, or a systems person too. If you're a systems person, you would also use this quite a bit as well. What is the probability of x successes occurring at fixed interval time if these events occur independently? So let's suppose I look for the next hour, and we had the drinking fountain working, and we'd expect 3 people to use the drinking fountain in the next hour. That's what we'd expect to do. You can model the Poisson distribution of whether figuring out the probability that 0 people use it, 1 people use it, 15 people use it, or 20 people use it. It's a common way of setting up a randomization of some sort of thing occurring within a very specific time. And I'm going to use the mean rate lambda, because I just like lambda better than mean mu for this problem. So we're expecting lambda people to do something within the next hour or day or whatever. So the mean is lambda, and the variance is lambda. And this is very strongly connected to the continuous exponential function, which is in Chapter 4. The exponential distribution is very important in insurance and other types of things. What's the probability until your next accident? What's the probability of how long you live? Those kind of things that insurers take a look at. So here we go. So the probability for the Poisson, we're going to use a lowercase p for Poisson. That's kind of unfortunate because that kind of reminds us of probability. But that's what and you have the number of number of successes based on this parameter lambda, and the lambda is the expected number within your fixed period of time. That's going to be your mean. And what this is equal to is the sum this is just equal to e to the minus lambda, lambda to the x over x factorial. So let's suppose I'm teaching class and I'm expecting 5 yawns in the class. What's the probability I get 4 yawns in the class? What was that? We're assuming that they're independent. So what's the probability of 4 yawns if we expect 5? What we'd have is e to the minus 5 to the 4th over 4 factorial.
Is that P? That P is Poisson.
That stands for the Poisson. It's, like I said, it's kind of unfortunate Where should I put the little loop?
Like on the line,
Put like a little loop here, like that?
or that,
Because like poison,
yeah.
like the group poison.
So is that not a probability then? Or is it still a probability that's in the Poisson family?
It's a probability in the Poisson family, yeah. I kind of like the little loop because it kind of separates it from the P. Jeff, did you have a question?
Yeah, why are both the mean and variance random?
That's the great thing about the Poisson distribution. It's the same. The reason why, I'll give you a hint why, because you have this exponential function, e to the x, and the derivative of e to the x is e to the x, and so it's something along those lines why that is. Did you figure out the probability? Anybody figure out the probability that I get 4 yawns instead?
Yeah.
What'd you get?
0.175.
0.175. So, like I said, this is very nice in terms of weight distributions, trying to figure out the probability, or doing simulations to see if your computer program can handle an onslaught of people. You have to make some pretty big assumptions, but it still does pretty well. The one thing that it does do as well is this result on page 129, some more bonus information. If you have a binomial distribution and you let the number of trials go to infinity as your probability goes to 0, so this is kind of a calculus idea, you might still let NP be constant, but you might let your N go to infinity and your P be go to 0. What happens is that if it approaches a value lambda, then your binomial distribution will approach the Poisson distribution. So rather than having 10 people, you might have all the people in the world come, and you still expect 4. Instead of doing, 5 billion choose 16 million, or whatever, you can just use the Poisson distribution to do that.
The calculus, like you said, is it kind of like L'Hopital's rule with indeterminate?
Yeah. Yep. L'Hopital's rules in there as well. Yeah. Okay. So you might connect with your team, talk about your take-home test. Remember, I answered questions up to 4 p.m. It's due on Monday. Make sure you start a new page for each problem. Any other questions? Okay, homework due tomorrow as well.